Yeah, so let's go back to today's course. And a brief summary of what we said the other time. We talked a lot about extrusion and how it takes place. We said that extrusion is the most popular technique, and it has several types of variants, different types of extrusion, and what happens at the end of the extruder, essentially. The two major types of extruders, but the most common are twin screw because they have a high throughput and less effect of viscosity. How the screws are modular, okay? How we design the screws in order to do different processes throughout the length of the extruder is something very important as well, okay? Because it alters what we call the residence time distribution, okay? And it's a whole kind of design. We won't get into details about that. We said that it is very characteristic in order to, let's say, separate different types of extruder is their length to diameter ratio, okay? So this is the length, and this is the diameter, okay? The larger the ratio, as you would expect, the longer the extruder. And we saw already a couple of very long extruders, very large extruders, such as this one or the one in the videos that we saw. The majority of times we use extruders in order to combine a polymer with something else, okay? And that something else can be several types of secondary substances, such as plasticizers, as we said, fillers and reinforcement in general, additives and colors, and sometimes even blending with a second polymer in order to attribute different types of properties, such as, let's say, recyclability or biodegradability, okay? And we said that the most characteristic, the most obvious materials that are used with an extruder are semi-crystalline materials, okay? Why is that? Because for the crystalline regions, we can melt them, crystallize them, and remelt them as many times as we want, without any obvious differences in their ultimate properties, okay? And that is a very, very important advantage for these materials. Yeah, we saw that we can do different types of we can do different types of recycling for our materials. And at the end, we have the dies that essentially provide us with different shapes at the end of the extruder. And in this way, we obtain different types of products, but all of them, as you can realize, they have simple geometries. Okay? Now, as I said, at the end of the extruder, several times we perform different types of processes in order to end up with different types of materials, okay? Or different types of applications. So if we want to fabricate thick polymer sheets, and I repeat, thick is the keyword here, we use sheet extrusion. And how sheet extrusion takes place? Essentially, at the end of the extruder, we have this 3-row stack where essentially we guide our polymer melt through the 3-row stack in order to form a polymer sheet, okay? A polymer layer, a polymer film. We can call them films as well, okay? And by controlling the force between the rolls, that is the distance between the rolls, we control the thickness. As you can realize though, we cannot make them very thin. So it's only for thick polymer sheets. We cannot make thin polymer sheets through sheet extrusion, because if we apply a lot of force between these rolls, okay, if we apply a lot of force, we can end up breaking the polymer melt, okay? We can end up breaking the polymer film, and we won't end up having a continuous polymer film the way we want it, okay? So that is why by seed extrusion, we create thick polymer sheets. Yeah, this is a seed extrusion line, as it's called in the industry. And this is how it looks, essentially. As I told you, it is very important that these rolls are very clean, polished, and smooth, because any problem that is present on the rolls, it will be then reflected on the ultimate product, okay? So the rolls have to be very carefully cleaned and very carefully maintained. Something that is very common in the industry is having two extruders and extruding them in the same region, in the same area, in order to create multi-layer materials. And the process is called co-extrusion, okay? It is relatively simple, and with this case, we create multi-layer materials for different types of applications, such as cables, or we can use, because of excellent barrier properties of some polymers, we can use them for food applications as well. Now, if we want to create thin films, such as plastic bags, and the keyword again now is thin films, we use what is called the blown film extrusion, okay? Sorry. So at the end of the extruder this time, we have this air ring, okay, where it blows air at the polymer melt, okay? And because it blows air with force when the polymer comes out, the polymer expands at the sides and creates this air bubble, okay? So the polymer film here is located here at the edges, at the ends, okay? And then it is guided through these rolls here and collected at the end by going through that direction, okay? So the keyword here is that we use blown film extrusion for thin films, okay? And what is done here is at the end of the extruder, we blow air at different pressures, okay? So the key here is controlling by controlling the air pressure, we control the thickness, okay? But in this case, we can make materials, continuous sheets of materials, much thinner than the seed extrusion. Yes, this is how it works. It creates bags, films, and sheets. It may sound very trivial or very not too important, all these type of materials, but as we said, the majority of polymers that are consumed globally correspond to these very, very simple applications, okay? Bin bags, supermarket bags, packaging materials, such as when you buy something to eat from a supermarket, it needs polymer to get packaged, okay? So we need thin polymer layers in order to package it. And these materials are many times created by film blowing or extrusion, blown film extrusion. You can see how large these setups are in an industrial environment. Okay, these are massive. They cost a lot of money, but once they are up and running, they produce tons and tons of materials. And we pretty much ended up here, which is a graph that I'd like to discuss one more time before going forward, because I remember there were some sound problems. I hope today we have resolved them. I have updated the application. I have updated my laptop. I did all I could essentially. I uninstalled and reinstalled the software. So I hope today we have solved it. So if we look at this graph of thickness over melt flow index. Does anyone remember what is the relationship between melt flow index and viscosity? Can anyone post in the chat, in WeCom chat, what is the relationship between melt flow index and viscosity? What is happening with Indeed, it's inverse. So the melt flow index is proportional to the inverse of viscosity. Okay. So when the melt flow index increases, the viscosity decreases. Okay. So if you want to have thick films, and thick films are expressed in this graph by these two, or even that one as well, experimental values. Okay, we can see that we need a low melt flow index that is high viscosity, and high viscosity is usually observed for polymers with high molecular weights. Okay, now if we want a material that have thin film, okay, it is relatively thin, its thickness is small, so we need a good flow of our material. Okay, so we need a high melt flow index that leads to low viscosity and low molecular weight. Okay, and of course, as I told you, extrusion is not always very simple, and we can have some problems with extrusion because generally we cannot create simple extrusion. Okay, we cannot create very complex shapes by extruder. And another problem, though, is this phenomenon that we discussed already, what is called melt elasticity. Okay, so melt elasticity originates from the fact that polymers behave viscoelastically. Okay, so essentially, when the polymers are in the melt state, polymers are fluid, that is the polymer melt. Okay. And because of the viscoelasticity, when we have strong elongational flows, such as during polymer processing, Swell and melt fracture are controlled by the Z average molar mass, which we said what is the Z average molar mass dependent on? What is the characteristic of the change that affects the MZ? What does the Z average molar mass essentially measure? Gives a distribution, let's say. Anyone from the polymers group? What affects the Z average molar mass? The Z average molar mass is affected by, wait, did I have an answer? Yes, the length of the chains, indeed. So the longer the chains, the more opportunities is for the chains to build up the stress, okay? Because once they're mingled in the melt state, okay, they can essentially sometimes when they come out, because they crystallize, okay, it's more often for them to form entanglements, okay? So when the material comes out, essentially it forms entanglements and swells more. Let's have a look at the die swell, essentially. We said already that it is the phenomenon in which the polymer swells as it leaves the die. So here we have, let's say if we have water, and here we have polymer, you can see that the initial diameter ends up being much larger in the case of the polymer compared to the case of a liquid that is stable structurally, okay? So the extrudate, essentially extrudate is the material that comes out from the extruder. Has different dimensions, okay? It has different size from the material we would expect if, according to the die size, okay? The die size, or okay, and the die swell essentially results from recovery of elastic deformation because the extrudate leaves the die before it crystallizes, okay? It's very important that the die swell affects the dimensional stability of extruded profiles, films, and fibers. Yeah, we saw that. This is a video that we saw the other time, so I'd skip it in order to maybe avoid any complications with sound. But I will try a couple of videos in a second. So the second phenomenon that we don't want when extruding a polymer, besides the die swell, is the melt fracture, okay? And the melt fracture is generally affected by the flow and the feeding rate, okay? The flow of the polymer. Okay, that is within the extruder. Let's see what's happening when we increase the flow rate. How do we increase the flow rate? By controlling the RPM of the screws, okay? So if we keep the feeding rate constant and we increase the RPM of the screws, we increase how fast the polymer travels throughout the extruder, we end up with melt fracture, okay? So this is for a liquid, let's say, that is not affected by essentially how much is fed, because it does not display viscoelastic characteristic, okay? So its dimensions, the dimensions of the material come out from the die are the same with the dimensions of the die. Now, in the second figure, here we have this phenomenon that we said already is the die swell or Varus effect. Okay, we already spoke about that. We can see that the dimensions are slightly larger than the dimensions of the dimensions of the die. Okay, but what is interesting here is that okay, we may have problems because of viscoelastic characteristics, but the surface is smooth. Okay. Now, if we increase more the flow rate, okay, if we increase more the material that comes out from the extruder while keeping the feeding rate more, we end up developing undulations, okay, developing not stable extrusion profile, okay. So these are called undulations. No smooth surface. And of course, if we increase even further the flow rate, we develop more pressure throughout the extruder, and by doing so, we create a number of irregularities on the surface of our material. So we end up having completely fully irregular, but also sometimes it stops because sometimes the the area here it can become blocked because of excess material. What does excess material mean? It means that we develop very, very high pressures at the end of the die and different flows, okay? And let's have a look at how a different flow looks in a melt fracture sample. You can see that we have two different types of flows. The first flow of the polymer comes out like that, but also there is a polymer, there is an amount of polymer that essentially is trapped here at the edges. And because of that, we have this melt fracture phenomenon. That leads to melt fracture. We said that the extruder has rough surface, short cuts, oriented at the machine direction, and helically around the extruder. Okay. As I told you, it can take place because of very fast feeding rate, very fast extrusion, flow, polymer flow, and also because of low temperatures. Okay, the polymer is not melt completely, and because it's not melt completely, it doesn't flow continuously. Let me write this down. We don't have. Because we don't achieve melt flow, pressure is developed at the die region. And because of different pressure, we have different flows, okay? And the melt fracture. Okay, now time to test if all these updates made any difference, okay? Let me try and show you a video of how melt fracture takes place. Please let me know immediately after I return to the iPad if you can hear me, okay? I stop sharing now. I share my PowerPoint. Where is my PowerPoint? This is my PowerPoint. Okay, you can see my PowerPoint.
Start timing it.
So you can see this is the polymer that's coming out, that's extruded in a sheet form, okay? And already here we can see that they are developing some different colors. The polymer changes color. You can see how now it's almost white because there is internal stress that's developed when extruding. And compare it with the beginning where here, okay, it was almost opaque. But because we're extruding too fast, okay, internal stress is developed and melt fracture takes place. And you can see that because of the melt fracture, we have irregular surface and irregular characteristics of our polymer. So we end up having a polymer where different parts of the polymer that we have extruded show different properties, okay? And that is something that we absolutely do not want. Okay, stop sharing. Now, the time of truth, guys. Let's see. Share. Please, can someone text me to let me know if you can hear me? Is all good? Can anyone make a sign or something like that? If you can hear me? Okay, I see you. Great. So we fixed this problem. Finally, let's wrap up the extruder. So as you can realize, we discussed extensively about the things that affect the extruder, and essentially we need to control a number of variables in order to ensure that an extruder operates as it should. Okay, so some of them include the screw speed. Okay, the screw speed essentially has to do with how fast the screws turn in order to make the polymer travel throughout the extruder. Of course, the feeding rate of the polymer is important because the more polymer it falls onto the extruder, the more busy the extruder is to melt the polymer and to also make the polymer travel throughout the extruder. But we need to know that the more polymer that we feed, the higher the friction is between the polymer pellets and the screws, and also the polymer pellets and the barrel, okay? And that leads to increased pressure. I'd say the same for the screw speed as well. The barrel temperature, as you would expect, is very important because we need to fully melt our polymer. Okay, the torque of the motor, okay, how strong our motor is, it's fine. The die pressure is very important because, as I said, we need to have a constant pressure in order to have a constant extrudate. Material temperature, yeah, indeed, they are connected. These two, essentially, it has to do with achieving a completely melt state, so the polymer flows, okay? And finally, the residence time distribution, we already spoke about that, is how long the polymer stays in the barrel. And in order to control that, we control the screws, okay? We control the screw design, we control the feeding rate, we control also the screw speed, okay? So in order to control that, we control screw design, screw speed, and feeding rate. Something that also affects the material that we end up getting is that we need to avoid contamination of polymer with other plastics, okay, obvious. And also something is very important is to dry effectively our polymers before feeding them onto the extruder. And why is that? Is because humidity or water can lead to, let's say, lower transparency and also lower ultimate properties. And that is why usually before extruding our material, we put them in an oven for, let's say, 4 hours, 5 hours at 70 or 80 degrees. And this way, moisture. Okay, we don't generally use much higher temperatures. Of course, we could reach, I don't know, 100 degrees, but 100 degrees several times for thermoplastics can be close to either their melting points or the glass transition temperatures, and we don't want to be within temperatures that are close to these, let's say, significant thermal transition temperatures in order to keep our material unaffected before extrusion. These are too technical, not too important. Don't pay too much attention to these. Also, in terms of processing temperatures, we said that along the extruder we have different temperatures because we also have an increase of the temperature because of friction between the pellets themselves, friction between the pellets and the screws, and friction between the pellets and the barrel. Okay, so all this friction ends up increasing the temperature, and that is why usually we don't put as maximum temperatures as we want, because the temperature is generally increased by friction throughout the extruder. Okay, let's move on. These ones are okay for you to have a read yourself. Any questions, please ask me. And now let's move on from the extrusion. We might have stayed a bit too long, but it's the most important technique, along with injection molding. But as you can see, there are more techniques for polymer processing, and the rubber compounding is usually done with this technique that is called two-roll mill. Okay, this technique takes place at room temperature. Okay, RT is room temperature, and it's essentially a very, very simple technique. Essentially, we feed our rubber between those rolls. Okay, say here we have two rolls. The rolls are counter-rotating. Okay, and we feed our rubber in there, and we also feed our rubber along with sulfur and other chemical agents. Why, can anyone tell me why do we do that? Why do we, let's say, just fit the rubber in there and take it out of the two-roll mill and create rubber materials such as those seats? Or, yeah, different forms of rubber. Usually we use seats and then we cut them or something. What is the purpose of sulfur and other chemical agents? I just saw your question, Peter. I'll answer it during the break. Why do we use sulfur and other chemical agents when processing rubber? Does anyone remember? We discussed it about it quite a few times so far. Very briefly, we will be talking extensively either tomorrow or Thursday about that. What is the purpose of sulfur and other chemical agents when processing a rubber or an elastomer in general? Theo says to cure the rubber. That is close, yeah. Anyone else? Any ideas? Why do we usually use sulfur and other chemical agents? Because we want to create crosslinks. Okay. In the case of rubber, cross-linking is weak. That is why we can extend the rubber at room temperature several times its original length. Okay. So we create these crosslinks, and afterwards we cure our rubber in the presence of temperature. Okay. So we mix the rubber with those cross-linking agents. Carbon black is usually used as a reinforcement. And then we create those chemical crosslinks, okay, by heating them under pressure and ensuring that these have taken place. Let's have a look at how rubber compounding takes place, and then we will stop for a break. Share screen, polymer processing, share. Let's go to the rubber. Where is it? There it is. Okay, this is how a machine looks. A two-roll mill, that's how it's called. Sometimes we can heat up the rolls, okay, in order to make our rubber a bit softer and help with processing, but it's not always the case because temperature of the rubber is generally increasing the more we put the material within this two-roll mill. Come on, when is he gonna process anything? You can see these are the two-roll mills. They're essentially counter-rotating. This is a piece of rubber. You see, we control the distance between the two rolls, and in this way we control the thickness and we control the size of the rubber sheet that we get. You see how smooth it becomes, and then we cut it and we put it again over there, you see, in order to ensure that mixing is effective, okay? So we roll it and then we feed it again between the rolls. Because of sulfur, generally, all rubber processing plants generally do not smell very good. So it's a very bad smell when processing rubber. Looks like a toy, but it's not actually a toy. It's a very industrially scalable technique. In order to cut these, we have these special knives, okay, and you cut them when processing them, and then you roll them again and feed them within this two-roll mill. You saw it, okay, that's pretty much it. Okay, pause. Okay, so that's how we process rubber materials in order to fabricate continuous rubber sheets, which we then stamp with knives and so on, or we cure them afterwards. Let's take a 10-minute break now, and we will continue in 10 minutes with a couple more polymer processing techniques. Okay, so let's get started with second part of today's course, and let's continue with another technique. It's called calendaring. Okay, this technique is relatively versatile because we can use it with for thick and average thickness materials. And also it is very important its versatility because it can produce thermoplastic films and also rubber films. Okay, that is how. Okay, this is a relatively simple calendaring process, but generally it looks like that. Okay, it passes through multiple rows in order to have better thickness control. Okay, and so what happens in an in an extrusion block? And we extrude this polymer, okay, which looks like that, and it's called Parison. Parison is that part. forms a bottle, okay? So air, so it's inflated to fill mold and essentially expands onto walls of mold. Sometimes, okay, sometimes molding, it's mold or mold. Okay, something like, I'm not sure which one is always the correct one, depending on if you're in the United States or in Britain or something. It's not important. However you write it, I'll accept it. I don't even know how to write it every time. Every time something different. So again, I repeat, extruder fabricates this partition, which is soft. Okay, it's not molten completely, but it's not liquid. So the partition, the mold closes over the partition. We have the compressed air. The air makes the partition expand towards the ends of the mold, the sides of the wall, and then we have this bottle that is produced. That afterwards, with certain specialized knives, we cut the excess material. Okay, this should be a video. So let me. Yes, this is a video showing how extrusion blow molding takes place. It's easier to show you these processes by video, so you realize how these processes take place in an industrial environment. You can realize that the blow molding process helps us make, I don't know, billions of bottles every day. So as you can realize, there are several lines in industrial factories that work simultaneously. So we have our polymer pellets. You see the white one and the yellow one is usually the pigment, okay, in order to give color to our polymer. This is the extruder, okay. So you can see the extruder, okay. Wait. Okay, this is the partition that I was telling you, okay. It comes out from this specialized die, and we control the pressure and the temperature so that this material is soft, but it's not in a molten state. So the mold comes in and closes, okay. The mold closed and took the plastic from there and moves it onto, you might have missed it, but moves it onto the gas blowing part. You see at the back here, you see that there is where air blowing takes place, and once air is blown within the mold, we have the fabrication of these bottles. Okay, here is where air is blown onto the bottles, and then we have the formation of the bottles after we open our mold. We cool down the mold, of course, in order to solidify completely our material. And then we want to cut any excess material, such as this one. So there are specialized knives. Okay, you see how they cut them. And always we collect these materials because what did we say? In the majority of these types of polymers, we can reprocess any excess material in order to make more bottles. Okay, so there's absolutely no losses throughout the process. So again, you see these materials are chopped down and reprocessed in order to create those bottles. This is how the cups are removed. And I want to show you one final part of this video, which is very important. This is quality testing, okay? Here at this part, there is in the industrial line, there is gas that is blown onto the bottle. And once the gas is blown onto the bottle, this machine essentially measures the pressure of the gas. If the pressure of the gas is lower than the pressure it puts onto the bottle, that means that there is a leak in the bottle. and that leads to a failure, okay? So let's have a look what happens. So here, air is blown onto the bottle. These materials had good pressure, these bottles had good pressure, so they are kept. This one, you saw, it was thrown away because probably the amount of pressure that was measured was not the one that was put in the bottle. Okay, so you see, this one was discarded. So we need to have a certain amount of quality control in order to know if every bottle is fabricated identically. So you can see how many plastic bottles are produced from an industrial line every time through extrusion blow molding. Stop sharing, share screen, here. Okay. As I told you, there are so many different types of blow molded products that we can produce, but what is common in all of these? They are all hollow. Okay, so that means that they have a hole, they are empty, their inside is empty, okay? So generally, the majority of blow molded products have to do with product containers that either can be in a liquid form or in a solid form or whatever, but still they are containers. Now, there is a different type of blow molding process that I told you, it's injection blow molding. The first part, essentially, we have these preforms, okay? These are produced extensively by injection molding. We will see in a bit how injection molding is created. And essentially what we do is we heat up these preforms, and again we blow air into the preform. Here we blow air in order to make them take the shape of the mold. Okay, this yellow part is the mold. As you realize, the most important part here is to have these preforms made by injection molding. We will see how injection molding takes place in a bit. Okay, so it's very similar to the previous process. Yes, and this is about injection blow molding. It is used for the fabrication of different types of bottles, and in the majority of cases where we have bottles for fizzy drinks or for water and so on, the polymer that we use is PET, polyethylene I think I wrote it correctly. So polyethylene terephthalate is preferred for its use on bottle applications because, firstly, it has very low permeability. Permeability shows us how gases can escape a polymer. Okay, so for polymer such as PET, it is very low, and that is why we prefer it for fizzy drinks. Okay, drinks which have carbon dioxide in them. Okay, so they have CO2 in them. You can see that polypropylene, for example, has 57. So carbon dioxide could escape from our polymer bottle, and essentially the drink won't have the same quality as in the case of PET. And also PET is thermally stable. It has a relatively high glass transition. I don't remember exactly now, but it's significantly higher than 40-50 degrees, which is a temperatures that are generally in the environment in the global environment in a very, very warm day. So even at this case, the PET maintains its structural integrity. Okay. Yeah, this is what we said, how injection blow molding takes place. We have these preforms. We put them in the mold, and then we close the mold and we heat them up with this stretch rod. Okay, so we heat them up, and then we blow air. Okay, and we fabricate these bottles. What is this? This should be a video. Not, it is a video. I don't share screen. Look how I want to show you with this video how big these facilities are. Called stretch blow molding. We're talking about massive facilities, huh? It's a huge industry. Okay, this one is extrusion blow molding, not injection blow molding. Ah, yeah, you perform the injection of the preform. Okay. So the preforms are created. This is the preform. Use pressurized air and fabricate those containers. Again, quality check the same with previously. You can see if air escapes, the materials are rejected. Okay, the end product is rejected, and you can see how fast the blow molded products are produced. Okay. Stop sharing the screen. Okay. This is how a mold looks. Okay. It looks a bit weird. Don't comment on that. But generally, this is how the end product looks. Blow molded products, we use them in the majority, as you can see, for different types of baffles. Now, let's move on to another very interesting technique that is called polymer processing technique, that's called fiber spinning. Okay. By fiber spinning, we can create polymer fibers of very fine diameter that show exceptional characteristics. And why is that? We will see that in a second. Okay. So in this case, we have molten polymer here. And essentially, extrusion of the hot melt, it takes through very small holes, okay, that are called spinnerets. These spinnerets are here, around here, okay. And usually we either extrude these in air or water, and then the fibers are essentially cooled down and wound up in a rotating speed. Because these fibers have very small diameter, okay, and we essentially stretch them, what do we achieve? We achieve a high orientation of polymer chains, okay? As a result of stretching. In this case, stretching takes place also during the wind-up, but also after post-processing. So we have the fiber after the wind up, okay, and we slightly stretch them afterwards in order to create these stretched oriented polymer chains, okay? So the chains look like that and not like that. We have three different types of fiber spinning processes. The one is this most straightforward. Essentially, we melt the polymer and we use the spinneret in order to extrude through these very, very small sized holes, okay? But also we have an opportunity to use with fiber spinning, let's say, equipment. We can use polymer and a solvent mixture. So we have dissolved polymer here. In these two cases, we have polymer plus solvent mixture, okay? So essentially, we dissolve the polymer into a solvent, okay, an appropriate solvent. We extrude the polymer with a solvent or into a liquid environment, which essentially leads to the solvent. Here, evaporate solvent. Or we extract the solvent by reacting it with something else. And in this case, we fabricate these fibers, okay? So let's have a look for polyethylene, for a very high performance polyethylene that is used in state-of-the-art applications. We need very high orientation, and also we generally use materials with high molecular weight. In order to have longer chains, okay, and higher number of chains. So in this case, the crystallinity of highly oriented material can be up to 85%, while in the case of regular polyethylene, where it shows low orientation, the crystallinity is lower than 16. Majority of the times is around, I don't know, 35 to 45%, okay, for regular polyethylene. So you can realize that with double the crystallinity, we can have very pronouncedly increased properties such as mechanical properties, thermal conductivity, chemical stability, and so on. Okay. Yeah, this is a very common process that takes place for ultra high molecular weight. Okay, and the important part of the spinning process is what I mentioned here. The spinning process leads to a molecular structure which contains a very low entanglement density, okay? So by having a very low entanglement density, we have oriented chains which are not entangled between them. And because they're not entangled between them, they create these continuous fibers. Okay, you can see that with increasing amount of drawing is essentially, once we have the fiber, we slightly pull it afterwards in order to induce even further orientation. And we can see that the more oriented our samples are, the better the mechanical properties of ultra-drawn polyethylene, okay? With increasing drawing, we have an increase in both modulus and strength to significant values. A modulus of ultra-drawn polyethylene can reach 100 gigapascals. That is massive, okay? That is very, very high. And also the strength around 3 gigapascals is also very significant. These are some commercially available fibers that are called dyneema, okay? You can see how much more strength over modulus they have compared to different types of fibers, such as carbon fibers, aramid fibers, glass fibers, and so on. Of course, the very high elongation, I should point out, the very high mechanical properties can lead to generally low elongation. So these materials are stiff, they are very strong, they have very high values of crystallinity, but they cannot be elongated a lot, okay? And as I told you, thermal conductivity is a property that can be very significantly affected by stretching our material. And essentially, polymers have almost zero thermal conductivity, okay? You can see that thermal conductivity of the majority of polymers is around 0.2 to 0.4 or 5 watts per meter Kelvin, okay? By stretching our materials, okay, we create these fibers or drawn tapes, okay, we can achieve metallic-like conductivity. So this is induced. So we create fibers or tapes. Tapes are like continuously drawn materials that are essentially, again, but wider than fibers. And you can see, because we have more oriented chains and much higher crystallinity, the thermal conductivity from 0.3 has increased to 65, which is similar to some metals, okay? That is more than one order of magnitude higher than the unoriented. 2 orders of magnitude. Yeah, these are some high performance fibers. So we can use them for fishing lines. We can use them in bulletproof vests and helmets and shields and so on. High performance applications such as in aerospace or nautical applications as well. Electrospinning is another process where, in this case, we do not create fibers in large dimensions, but we create nanofibers, okay? So in this case, what happens, we have a polymer solution here, and we apply high voltage to this region here. And because we have this current collector at the end, we create this difference in voltage between the liquid droplet and the collector, and that ends up creating these fine fibers by producing what is called these Taylor cones. And because of the stretching between the differences in voltage between the collector and the spinner, we have these very, very thin types of fibers, okay? I don't want you to remember the process for electrospinning. It's not something I will ask you for exams, okay? And electrospinning for the creation of nanofibers has produced a number of very interesting results, and that is why people have looked into essentially expanding this process from this simple one where it produces only one fiber to this one, what is called Nanospider Electrospinning, where essentially we have multiple fibers that are essentially coming out from different regions of a setup, essentially. And here we have a roll-to-roll process where essentially the collector continuously, the supporting material continuously passes over the collector and collects new material, and so on. You can see how fine the electrospun fibers are, okay? Because look how this is a human hair. This is a pollen, grain of pollen. And these are nanofibers at the back, okay? So you can realize how much smaller, finer, thinner they are. And with the advent of nanotechnology, we can take advantage of these electrospun fibers for a number of applications, such as sensors, tissue engineering, filtration media. Sometimes we use them for their electronic and optical applications, and so on. Okay? Now, let's go to injection molding. We have only 10 minutes, but we will continue tomorrow as well. Injection molding, as I told you, is the second most important polymer processing technique, okay? Along with the extrusion, they constitute 70 to 75% of the process, okay, of the polymer processing techniques. And the majority of polymer processing industries are using either injection molding or extrusion, okay? In a sense, injection molding as the main part of the machine is similar to the extruder, where essentially what we do is we melt our polymer, okay? We make it travel throughout a barrel, and then we fill a mold with our molten polymer, okay? So as you can realize, the shape and the dimensions and the design of the mold is very, very important for the stability of the material that we produce, okay? The products that we produce by injection molding. What is something that is very characteristic of injection molding is that it has a skin core structure. We will discuss about that tomorrow probably. But I should point out again that injection molding depends absolutely on the mold characteristics or design. The advantage of injection molding is we can produce materials with complex shapes and it can produce materials that are ready to be used, okay? After it comes out from the injection molder, they're ready to be used. No post-processing is required. So, no post-processing. Okay, so let's have a look at how an injection molder looks. This is a machine, an injection molding machine. Essentially, as I told you, up to this point, essentially, it looks very similar to an extruder, okay? So what we do is we fill the hopper with pellets. We have the screws here that essentially make our polymer melt. And then what we do is similar to a vaccine, essentially. We inject the screws onto the mold, okay? This is the mold here. The mold is consisting from a positive and a negative side, and one side of the mold is constant, So it's fixed pattern here, and one is moving, okay? So we have the fixed pattern here, we have the moving here, so closes and opens. Once we fill the mold, we cool it down, and then the moving pattern opens, and essentially we fabricate what is our demanded material, okay, demanded product. So here we use heat at temperatures commonly higher than the melting point of our material, okay? So here we fill the mold with a polymer. So this mold tool is filled with polymer. And injection molding is a very versatile materials. It's a versatile techniques. Majority of the times it's used to process thermoplastics, though, as with extrusion. Okay. As I told you, it's very important to have a very accurately fabricated molds. Okay, because any problems in the mold will result to significant problems with your final polymer materials. So the fabrication of molds for injection molding is one of the most costly parts of injection molding. So the fabrication of complex molds is very expensive, and that is why industries usually try to fabricate as little as possible molds in order to maintain the similarities in their product. Okay. Injection molding is used for a number of parts, from small components to wheelie beams and entire body panels of cars. So it is used extensively for very significant types of polymers. This is an injection molding machine. It's not huge, but it's not a very small one. There are different types of injection molders, as you understand, similar to extruders. And we said that for the extruders, we characterize them over the length to diameter ratio. For injection molders, we essentially rate them by tonnage, okay? So machines and what does tonnage mean? Means it's the amount of the clamping force, okay? What is the force that we put in order to make the polymer travel throughout the injection molder towards the mold, okay? This process, that is the force that is applied from the injection molder in order to make the material fill the mold, that is the tonnage, okay? That is the amount of clamping force. And this force is calculated by this very simple equation: force equals to pressure times the area, okay? Pressure is the injection pressure, and A is the cavity area of the mold, okay? The tonnage can vary significantly from less than 5 tons to 5,000 tons, where high figures in a very small number of accuracy. And usually, we can have a very large variation in the amount of polymer that we injection mold. It can vary from 20 grams, that is for academic usually labs, to 20 kilos for very large industries, okay? Let's have a look once again how injection molding takes place. I told you that we have the feeding zone. We feed our polymer pellets here, okay? Here throughout we have heat, okay? We have increased temperature in order to have the polymer in a melt state, okay? So we feed the polymer, it's molten here in this region, and this essentially this screw goes back and forth, okay? When it goes to the front, it pushes our molten polymer to the mold, okay? This is a mold. So the polymer fills the mold here. And as I told you, the mold consists of a positive and a negative side. So there is a reflection of the mold, essentially. We have a stationary platen that is not moving, and a movable platen that's moving. Once we fill our mold, we have a cooling system usually. So the polymer is solidified within the mold, and by solidifying within the mold, then we use the movable pattern to remove it from there and be able to use it. Okay. And these are some products that can be injection molded. You can see that there is a very large variety of material that can be injection molded. I told you that we can injection mold from very, very simple shapes to very complex shapes, okay? And that is why injection molded is very, very popular in polymer processing industry. And with that, I'd like to thank you for your attention today. Thanks for coming. We will finalize injection molding and a couple of simple techniques tomorrow. I'll probably prepare a couple of multiple choice questions for the polymer processing and maybe also the blending. I don't remember if we did multiple choice questions to revise a bit.